Hi, I'm Jeff Groh. Welcome back to Calculus 2. Today we're going to talk about conics, their parameterizations, and polar coordinates. We'll begin with a short review of what a conic section is. If you have a cone, and let's suppose that you slice it right through this point, that single point is a degenerate conic section. A single point. Sections are cuttings or slicings of things. If you take that plane and pass it through the cone here, in a way that is normal to the axis, then what you end up with is a circle. So a circle is a conic section. If you angle the plane, it can cut it in an ellipse. So an ellipse is a conic section. If you cut a cone parallel to an edge, you end up with a parabola. If you cut a cone exactly on the edge, you end up with a single straight line. And this too is a degenerate conic. If you cut it at a steeper angle, intersecting both ends of the cone. By the way, the upper part of the cone is referred to as the upper nap. And then we have the lower nap as well. If you cut the cone in this way, you end up with two curves forming a hyperbola. At any angle steeper than parallel to the side, you end up cutting both naps of the cone, and you end up with a hyperbola. There is one more case. The final way that you can cut a cone is straight down the middle in this way, and the intersection would be two intersecting lines. This too is a degenerate case. In pre-calculus, you were taught that a conic is any solution to an equation of this form, in particular, if b squared minus 4ac is less than 0, you end up with an ellipse. If b squared minus 4ac is equal to 0, you get a parabola. And if b squared minus 4ac is greater than 0, you have a hyperbola. You are also taught that a parabola is a set of points in the plane that are equidistant. I love that word, equidistant. From a fixed point called the focus and a fixed line called the directrix. The picture is like this. You have a line and a point. Here's your directrix, there's your point. The set of points that are equidistant, I'm drawn it to look that way, but if these two distances are the same, then at each point on this, if these two distances are the same for each point as you move along the curve, then the curve is a parabola. We'll derive an equation for a parabola. Let's put the directrix here. At y equals minus p, and we'll put the focus here at the point 0, p. If the point x, y is on the parabola, then this distance must equal this distance. The distance here is the distance y plus p. The distance between the point 0p and the point xy is found using the distance formula. And I give you the equation of a parabola. Well, actually, I guess we can simplify this a little bit. If we square both sides, we can get rid of the square root. Foiling out the left-hand side, we have y squared plus 2py plus p squared. On the right-hand side, we have x squared plus y squared minus 2py plus p squared. We can subtract y squared from both sides and p squared from both sides. Moving the 2py over to the other side, we have 4py equals x squared. I give you the equation of a parabola. Whatever the coefficient of the degree 1 term is, that is 4p, where p is the distance from the vertex to the focus. This 4p has another significance. If we draw a line segment through the focus parallel to the directrix, that line segment is called the Lattice Rectum. It allows us to more accurately draw how wide our parabolas are. The question I have for you is, how long is this lattice rectum? It's pretty easy to find out. What we need to do is find the intersection between the parabola and the line y equals p. We'll find the intersection here. So if y is equal to p, we have 4p squared equals x squared. So x will be plus or minus 2p. That means you go 2p units this way and 2p units this way. So the entire distance is 4p. So the lattice rectum has length equal to 4p, 4p being the coefficient of y. So whatever the coefficient of y is, that's the length of the lattice rectum. Here's an example. Suppose I have 8y equals x squared. The vertex, whenever they're untranslated like this, is at the origin. For P is 8, which means P is 2. That puts the focus at the point 0, 2. Since 4P is 8, we're going to go 1, 2, 3, 4 units this way, 1, 2, 3, 4 units this way. We have an 8-unit wide lattice rectum. That means the curve is going to go like this. You may, of course, translate these things all over the plane, or turn them on their sides. Rotating them takes a bit more effort, as you might recall from pre-calculus. I would like to look at the reflective property. Of parabolas. You might have learned that if you have a parabola with a focus, if you make a mirrored surface the shape of that parabola, then the light will bounce off and collect at the focus. This gives you one way of concentrating light from a diffuse beam into a strong light signal at a particular point. This is the principle behind the reflecting telescope, invented by Sir Isaac Newton. This is also the principle behind satellite dishes, collecting radio waves and bouncing them, concentrating them at a point so you get an amplified signal. This is also used in automobile headlights, where you have a light, which is a strong light source, emitting light, bouncing off of a parabolic mirror, forming a beam of light coming out the front of the car. You may have even seen these at science exhibits. For instance, at the Houston Museum of Natural Science, they have set up a couple parabolic dishes, and if you have one person at one side speaking here, their sound waves will be collected on the other side. Even if there are a lot of noisy people in between, yelling around and running around, making a lot of noise, if this person whispers, their whisper can be heard as though the person is talking into their heads at the other side. They also have one of these outside the Science Museum at Tampa. You may have heard of these reflecting properties of parabolas before, but it's about time you saw a proof of the reflective property for parabolas. Let's draw the graph so that the vertex of the parabola is at the origin. The focus is at the point 0, P. We'll draw a light ray coming down along the vertical line x equals a. That should strike the line here and be reflected off down through the focus. Drawing the tangent line, the angle of incidence, theta, should be the same as the angle of reflection, theta. If we call this alpha, then alpha is pi over 2 minus theta. Note that the slope of the tangent line is the tangent of alpha, or the tangent of pi over 2 minus theta. Using the cofunction identity, that's the cotangent of theta. Drawing a horizontal line over from the focus and a vertical line here, we have a right angle. Since vertical angles are equal, this angle must also be theta, and hence this angle must be alpha. If that's alpha, then this supplementary angle will be pi minus alpha, and this angle then will be pi minus theta minus pi minus alpha, which is alpha minus theta. But recalling that alpha is pi over 2 minus theta, this angle will be pi over 2 minus 2 theta. That means that the slope of this other line will be the tangent of pi over 2 minus 2 theta. And by the cofunction identity, that's the cotangent of the double angle 2 theta. So I now know the relationship between the slopes of, first of all, the tangent line, and second, the line going through supposedly through the focus. We have to prove that this line goes through the focus. That's the goal. The equation of this line, given the parabola 4py equals x squared, if the parabola has the equation 4py equals x squared, then the equation of this line should be y minus whatever the y value is here at x equals a. The y value should be a squared over 4p equals m2 times x minus a. Our goal is to prove that if x equals 0, then y equals p. We need to show that this line passes through 0p. So we'll set x equal to 0 and solve for y. Moving this term over, we have this expression where m2, you will recall, is the cotangent of 2 theta. We have cotangent theta is m1, but m1 can also be determined by the derivative. 4p dy dx equals 2x, so that the slope dy dx is x over 2p, canceling a 2 from each side. Evaluating at x equals a, we have m1, which is a over 2p, keeping in mind that this is equal to the cotangent of theta. We have only to show that this expression for the y-coordinate of the y-intercept of that second line is equal to p, which should follow from this other equation, cotangent theta is a over 2p. So we need a double angle identity for cotangent. You might recall that the tangent of 2 theta is 2 times the tangent of theta divided by 1 minus the tangent squared theta, which means that the cotangent of 2 theta is 1 minus the tangent squared theta over 2 times the tangent of theta. But we can figure out the tangent of theta. The tangent of theta is 2p over a. That means cotangent of 2 theta is 1 minus 2p over a quantity squared over 2 times 2p over a. So how does this expression simplify? Well, we can invert and multiply. Inverting will have 1 minus 4p squared over a squared times a over 4p. Distributing and writing it up here, cotangent 2 theta will be equal to a over 4p minus, on the second term, a 4 and a p will cancel. We'll have p over a. Making this substitution down here, the y-intercept of that secondary line will be a squared over 4p plus a over 4p minus p over a, all times minus a. You can now see that if you distribute one factor to each term within the parentheses, this term will cancel with this term, and we'll be left with p exactly as needed. Ellipses are defined in a similar fashion. For an ellipse, you have two foci, and for an ellipse, the sum of distance 1 from the first focus to a point on the curve, and then distance 2 to a second point on the curve focus, is equal to a constant, 2a. You can see that if we choose our point to be on one of the vertices, this distance is most of the distance across this major axis, and then the distance back would give you this distance on the other side. If we define half the major axis to have length a, then the sum of these must be equal to the length of the major axis. A set of points in the plane R2 such that the sum of distances to two fixed points called foci is a constant is called an ellipse. One can easily derive the formula for ellipses centered at the origin. The foci at some points C and minus C, the vertices at A and minus A, so that the major axis has length 2a, the minor axis, the smaller of the two, has a distance b from the center, and it turns out it's pretty easy to show that if these distances have to add up to 2a, then this side is b, this side is c in length, and this side is a, that a squared equals b squared plus c squared. Or in other words, c squared is a squared minus b squared. Don't forget it's a minus on the ellipse. There's one more important measure for ellipses, and that is the eccentricity. denoted by a lowercase e, its measure is c divided by a, where c is the distance from the center to a focus, and a is the length of the semi-major axis. What is the formula for the area of an ellipse? Well, if x squared over a squared plus y squared over b squared is equal to 1, then y is plus or minus b times the square root of 1 minus x squared over a squared. If we integrate from minus a to a, positive b times the square root of 1 minus x squared over a squared, we'll have only the upper half of the ellipse, because we'll have chosen the positive square root. If we double that, we'll get the bottom half as well. So to find the area of the ellipse, all we have to do is evaluate this integral. What is the method of integration? Since we have the difference of squares under a radical, this is definitely a trigonometric substitution. But first, let's simplify this just a bit. The integrand is an even function of x, and we are integrating from negative a to a. Whenever you integrate an even function from negative a to a, you may as well integrate from 0 to a and double. So this is going to be 4 times the integral from 0 to a. I'll move the b out. Square root of 1 minus x squared over a squared dx. To find the substitution, you take the square root of the variable term, x divided by a. In this case, that will be equal to sine theta, so that 1 over a dx is cosine theta d theta. We don't have a 1 over a dx, we have just dx, so I'm going to move this a to the right-hand side. The integral is transformed into 4ab. Note that if x is equal to 0, then theta must be 0. And if x is equal to a, sine of theta will be 1, which means the angle is pi over 2. We'll have the square root of 1 minus sine squared theta, and dx is replaced by a. We've already moved the a out. Cosine theta d theta. 1 minus sine squared is cosine squared. The square root of cosine squared is normally the absolute value of the cosine of theta, but we're on the first quadrant, so cosine will be positive anyway. So this will end up being cosine theta, so we'll have cosine squared theta. Which must be positive because we're squaring. We need to use the half angle identity. Recall that cosine squared theta is 1/2 times 1 plus cosine of 2 theta. We have 4ab over 2, integral from 0 to pi over 2, 1 plus cosine of 2 theta d theta. Now, the period of cosine 2 theta is 2 pi divided by 2, or just pi. If you look at the cosine function reduced to having a period of pi, if you're integrating from 0 to pi over 2, you got nothing. So this term gives us exactly no part of the answer. We're left with 2ab. If we integrate 1 on an interval of length pi over 2, any constant on an interval of some length gives you whatever that height is times the length of the interval. Height times width gives you the area of a rectangle. in this case 1 times pi over 2. The area of an ellipse is pi a b, where a is the length of the semi-major axis and b is the length of the semi-minor axis. Note that if a and b are equal, then you're dealing with a circle, and the common value of a and b will be equal to the radius. And this formula reduces to pi r squared, the area of the disk in that case. Hyperbolas are defined similarly to ellipses, but for a hyperbola there are 2 foci, and instead of taking the sum of distance 1 and distance 2, we take the difference to equal 2a. The set of points in the plane R2 having a common difference in distances to 2 fixed points called foci is called a hyperbola. From your experience in pre-calculus, you should recall that if you go a units this way, b units this way, you draw a little rectangle and connect the dots on the corners, then x squared over a squared minus y squared over b squared equals 1 will be an equation for a hyperbola that opens around the x-axis. Make the curve asymptotic to the asymptotes, go figure. The foci being at the points c units this way and c units this way, where c satisfies c squared equals a squared plus b squared, plus this time for the hyperbola. For hyperbolas, the eccentricity, also c divided by a, will be strictly greater than 1. For the ellipse, the eccentricity is always between 0 and 1, and equality with 1 is the case of a parabola. One of the most useful forms by which we can describe conics is in polar form. These are very useful in astronomical applications. You'll recall Kepler's first law is that planets move around the Sun in the shape of an ellipse. Objects that are gravitationally captured by some other object will move in an elliptical shape around the object that they orbit. Objects moving at exactly the escape velocity will move in the shape of a parabola, and those moving faster than the escape velocity will move in the shape of an hyperbola. So what objects move faster than escape velocities? Well, we've seen certain spacecraft that are launched and then accelerated by being gravitationally attracted to first Venus. They get slung off of Venus back past Earth. As they pass back across the orbit of Earth, they move around the Earth in the shape of a hyperbola. There is an object of some interest. In 1957, there was a nuclear explosion at the bottom of a well in Nevada. It was intended to be a very small explosion, but it went off much bigger than anticipated. The bomb was 500 feet down in a well colonnaded with cement, and it had a 4-inch thick iron plate over the top. Video during this explosion was taken at several million frames per second, and the iron plate was captured in an image estimated to be moving at 6 times the escape velocity from Earth, perhaps 150,000 miles per hour. This object, this steel object, may have been the first man-made object to not only go into orbit, but to perhaps leave the solar system. What likely happened, though, is that that iron plate experienced so much friction as it rose up through the atmosphere that it was evaporated and turned into a bunch of iron oxide in the atmosphere as it went up. To describe the polar form of conics, I'm going to make a new definition. And this definition will encompass all of the conic sections, not just one at a time. This definition has a directrix and a focus. And we're going to look at the distances between points on the curve and the direct distance from points on the curve to the directrix. These two distances, d1 and d2, are not necessarily going to be equal. In fact, they're assumed not necessarily. These distances, d1 and d2, are not necessarily equal. In fact, they are assumed to have a constant ratio, and that constant ratio will end up being the eccentricity. So if d1 is smaller than d2, you end up with an ellipse. If it's equal, you end up with a parabola, go figure. And if it's greater than 1, then you end up with a hyperbola. A set of points in the plane having a common ratio to a fixed point called a focus and a fixed line called a directrix is called a conic section. The ratio is called the eccentricity, and if E is less than 1 but bigger than 0, it has to be 0 or bigger, then it's an ellipse. Oops. If it's equal to 1, you have a parabola. And if it's greater than 1, you have a hyperbola. To create an equation describing this polar form for conic sections, I'm going to put my directrix at x equals minus p, where p, as I'm assuming, is a positive value for now. The focus is going to be at the origin. So whatever my conic section is, it's going to pass like this. This is really useful for describing astronomical situations where you place, say, the sun at the origin and the planet moving around it like this. If we have some point xy, also called r theta, then the first distance is r. That has to have a ratio with this second distance, which is p plus x, but x is r cosine theta. This ratio must be the eccentricity E. We can then solve for the polar equation of a conic section by solving this equation for r as a function of theta. Multiplying the denominator over to the right, we have r equals e times p plus r cosine theta. Distributing, we have pe plus re cosine theta. We'll move the r term to the left and get r minus re cosine theta equals pe. Factoring r out, and solving for r, we have pe divided by 1 minus e cosine theta. I give you the polar form of conic sections. You'll see these in other forms. R equals pe over 1 plus or minus e cosine theta, or pe over 1 plus or minus e sine theta. A more general version might be pe over 1 minus e cosine of theta minus some rotation angle theta naught. I'd like to show the graphs of some of these conic sections. We'll define p to be 1, e to be 0.8. Oops. And we'll plot this p times e divided by 1 minus e times the cosine of theta, where theta goes from 0 to 2 times pi. Scaling will be constrained. We'll change the view to -5 to 5, -5 to 5, and thickness equals 4, color equals blue. Oops, I forgot to set my coordinates. Coords equals polar. And here we have ourselves a nice little ellipse. Notice if I make the eccentricity smaller, not only does it make the figure smaller, it makes it more circular in shape. So to make the figure bigger, you could multiply p by a larger, you can make p a larger value. Notice that if the eccentricity is equal to 1, you end up with a parabola. And what happens if you make the eccentricity equal to 3? It actually has a plotting defect where it connects some far points way out on each side by these lines, but these lines approximate then the asymptotes for the hyperbola. Let's go back to our ellipse with an eccentricity of 0.8. I'd like to show you something. What happens if I subtract, say, pi divided by 6? Notice that it just rotates it through an angle of pi over 6. Rotating conics in polar coordinates is as easy as subtracting the rotation angle from the variable theta. So if I want to rotate through an angle of pi over 2, you can see that we have rotated this easily just by subtracting pi over 2 from the angle theta. This might aggravate you a little bit, considering how difficult rotation of conics was back in pre-calculus. Do you remember that? Those were big problems. Each problem, when you were fired up and ready to go, would take you at least 15 minutes. Now it takes you as long as it takes to change the value of this angle. I made a PowerPoint presentation that I think might amuse you. It's titled "To Infinity and Beyond." Johannes Kepler. Johannes Kepler said that a parabola is nothing more than an ellipse having a focus at infinity. If you think about that, that's complete nonsense. What does it mean for some curve, some ellipse, to have a focus at a point called infinity that is not even defined. Infinity is not defined. How could this make any sense whatsoever? But let me give you an animation showing you the plausibility of Kepler's argument and maybe a better way of formulating the statement that he has made. Here we have a sequence of ellipses having a focus that tends to infinity. And the curve, the parabola, shown in black, is the pointwise limit of those ellipses, shown in red. The value f is the eccentricity, by the way. Should be e, but it's called f. So it makes more sense to say that a parabola is the pointwise limit of a family of ellipses having a focus that tends to infinity. However, we may make sense of Kepler's statement by actually defining infinity, which I intend to do. We're going to look at the stereographic projection. Suppose I have a sphere sitting atop a plane. I can associate points on the sphere, S, with points on the plane by drawing a line segment. The beginning of the line segment is at the north pole of the sphere, and the ending of the line segment is at the point P in the plane. The line segment will initially be inside of the sphere, but it's going to pop out of the sphere at the point S. That point where the line intersects the sphere will be associated with the point P on the plane. We'll pretend that they are in fact the same point. This, by the way, was used by ancient astronomers. This form of projection was used by Ptolemy to project points on a spherical globe onto a plane for map making. One thing you should note is that the farther that point P is out in the plane, the higher the point S is up on the sphere. Do you see that? If the point P is moved way out, then the point S is going to be pretty high up on the sphere. The farther that point P is out, the closer that point S is to the North Pole. As you send P to infinity in any direction at all, the point S tends to the North Pole of the sphere. The North Pole is the point at infinity. In fact, we can define it to be so. This point at infinity, there it is, it's a well-defined point. It's this point on the sphere. It doesn't correspond to a point in the plane, but on the sphere, there it is. Now, an ellipse down here in the plane will correspond to a curve up here on the sphere, which we'll call an ellipse. A parabola in the plane corresponds to another curve on the sphere. Note that the parabola has two branches down here in the plane, and those branches on the sphere both converge to the point at infinity on the North Pole. For a hyperbola down on the plane, we get some interesting curve up here on the sphere. The four branches in the plane that tend to infinity all converge to the point at infinity on the North Pole. Now I'm going to show you on the next slide an animation showing a sequence of ellipses having a focus that is sent to infinity and beyond. As you'll see, as that focus goes to infinity and then beyond, you end up with hyperbolas on the other side. The red dot is that focus that is being sent to infinity. As the red dot reaches the North Pole, we have a parabola, but as we go beyond the North Pole, we end up with hyperbolas, and that focus comes back from infinity on the other side. So we arrive at another statement that is attributed to Kepler. A hyperbola is nothing more than an ellipse having a focus that has gone to infinity and back from the other side. And we're seeing that literally being true, especially if you consider this happening on the sphere, the stereographic projection.
The stereographic projection was known to Ptolemy in the 2nd century AD. Riemann, instead of using the xy plane, he used the complex plane, and the sphere then is called the Riemann sphere, to which you may add a number called infinity on the North Pole, and that begs, of course, the question about the arithmetic of infinity with complex numbers. Alexandroff discovered the topology of the one-point compactification of the plane, that is, that sphere.